All right, welcome to you guys that are here. Because of the length of this exam review, I probably won't have time to ask a lot of questions. I'll mostly be working through it on my own. But of course, if you have specific questions, or if I do ask a question, feel free to unmute yourself or type in the chat an answer or a question that you have, and I'll be happy to answer those. I'm here for you guys, whatever you guys need. So we'll go ahead and get started. But like I said, if you have any questions, let me know. Otherwise, I'll mostly be working through it on my own. Okay. So in which molecule does the stereocenter have the same configuration as the molecule shown below? So what we're going to want to do is find the configuration of this molecule and then determine which of the others have the same configuration. Okay, so we want to prioritize these groups first of all. And we know that we have a hidden hydrogen right here. So our oxygen is going to be number 1. Hydrogen is number 4. And then between this carbon and this carbon, we want to write our 3-letter code. This carbon is bonded to one other carbon and 2 hydrogens. So the 3-letter code would be carbon, hydrogen, hydrogen. Whereas this carbon over here only is bonded to hydrogens. So our higher priority group is going to be this one on the left and then this one. A little trick I like to use for this is if whichever side has the longer carbon chain, this way or this way, will be your higher priority group. So the longer chain was on the left, so our higher priority group is on the left. Okay. Now our number 4 is not going to the back. So we need to move number 4 to the back. Then come out here and redraw this with 4 there, and we'll swap it with 1. So the 1 is going to the front and keep 2 and 3 the same. Now we draw which direction this is going. So this is going to be pseudo what? Does anyone know?
Pseudo S.
Perfect, pseudo S. So our original is going to be R. Okay, now that we've established that our original is R, we can go ahead and work through the rest of these and figure out which ones have the same configuration or which ones are R. Okay, so we have a very similar structure in our first one as our example. So we can just, again, say that's our number 1, our number 4, number 3, and number 2. We can swap our 1 and 4. Two and 3. Okay, now this time it's going this way, which means pseudo R. So our original is S. And that means this is not the same configuration. Okay, let's do it again for the second one. OH is going to be our number 1. This is going to be our number 4 because it's the shortest carbon chain. This is our second shortest carbon chain, and this is the longest. Okay, so again, that's an easy way to determine if you're determining between carbon chains. The longest one will be your highest priority. Okay, so now we need to make sure our number 4 is in the back, which it is not. So we'll redraw it down here. Put our 4 on dash. Swap it with our 3. Okay. So this is going counterclockwise, which means pseudo S, right? And that means our original is R. So this one checks out. Okay, let's move on to our next one. The way I like to think of Fisher projections, which is how this molecule is drawn, is I like to think of our wedges like a bow tie. Okay, so when you're looking at these, the ones that are horizontal are wedges, and it looks like a bow tie. That's how you remember it. And then the ones going up and down are dashes. Okay, now let's label the priority here. We've got obviously our oxygen is number 1 and hydrogen is 4. Our longer carbon chain is a higher priority. So that's how we number them. Our number 4 is not going to the back, so we need to redraw it. Where we can swap 2 and 4. And we'll keep 3 and 1 the same. This is pseudo R, okay? How I like to remember R is going clockwise, is when you write an R, the circular part, when you start drawing it, goes clockwise, around like that, okay? So that's how I remembered that clockwise means R, okay? Just a little hint there. So pseudo R is clockwise, which means our original is S, which means this one is not like our original molecule. And last one here, we've got oxygen as our number 1, got a hidden hydrogen as number 4, a methyl group and a propyl group. So our propyl group is going to be bigger, number 3. We need to swap our 3 and 4. This is going counterclockwise, which means pseudo S. That means our original is R. So this one checks out as well. Any questions on how to accomplish that problem? No, we're okay. All right. Moving along. How many stereocenters are present in 3-terbutyl, 4-isopropyl, 2,5-dimethylheptane? Now that sounds like a mouthful, but we just need to break it down. So what is our parent chain? How many carbons long?
7.
Perfect. We're going to draw a 7-carbon chain. Okay. And number 3, we have what? Terbutyl. Okay. And then number 4, we have an isopropyl. And we have 2,5-dimethyl. So at carbon 2, we have a methyl group, and at carbon 5, we have a methyl group. Okay. So this is our structure. Now we need to determine how many stereocenters are present in this molecule. All right. So what defines a stereocenter? What are the characteristics of a stereocenter? Does anyone know? Okay, so we have to have a carbon. Okay, all stereocenters are carbon-based, and it's a carbon that is sp3 hybridized, which means there are no double bonds and no triple bonds directly on that carbon that we're looking at. Okay, so no double, no triple bonds, and we can ignore CH2s and CH3s. Okay, and the reason for that is because we have to have 4 different atoms around our central carbon. Okay, and so we can ignore CH2 and CH3 because they both have multiple hydrogens around them. Okay, so can this one be a stereocenter, that carbon?
No.
No, because it's CH3, right? Mm-hmm. So we can ignore that one because there's 3 hydrogens around it. We can ignore this one as well. What about this one? What do we think?
I think so, yeah.
Okay, let's talk about the 4 different things bonded around it. So we've got a hidden hydrogen. Let me just draw it off like this. We have a CH3, a CH3, and a C bonded to other carbons, CH basically. Okay. So because that has two of the same groups attached to it, it is not a stereocenter. Okay.
Okay.
Does that make sense?
Yes.
Perfect. All right. So now we move on to this carbon right here. So it's an sp3, no double bonds, right? So that's good. It's not a CH2 or CH3. Does it have 4 different groups around it? Okay, so we have a hydrogen, carbon, carbon, carbon. But are these carbons different from each other? Yes. Okay, so that does make this one a stereocenter. All right, so yes, that one is a stereocenter. So that's one. Is that making sense how to determine if something is a stereocenter?
How are those two carbons different? Those ones you just did?
Yeah, let's talk about it. So we're talking about these two, is that what you're saying?
Yeah, yeah.
Okay, so let's write the 3-letter codes for these carbons, okay? 3-letter code here is carbon, carbon, and hydrogen. So like this 3-letter code is carbon, carbon, and hydrogen. Okay, then we keep moving out. We say, okay, let's write the 3-letter code here and here. This first one is carbon, carbon, hydrogen as well. But the one at the top is just hydrogen, hydrogen, hydrogen.
Oh, I see. So you go to the next one after.
Yeah,
So,
you keep moving down the chain to make sure that they're different from each other.
oh, I see. Okay.
Perfect.
Thank you.
You're welcome. Perfect. So, glad we got that cleared up. I should have had the molecule pre-drawn, so then I wouldn't be able to erase it. All right. So we said this one is a stereocenter. Okay, how about this one? We could probably move through these a bit quicker. Yes or no?
Yep.
Yep, perfect. What about this one?
No.
No, right? Because we have 2 CH3 groups. Okay. So that one is not a stereocenter. This one's a CH2, so we can ignore it. CH2, ignore CH3, so we can ignore it.
I think there's one more on that one.
Oh, let's see, we did have
About 5.
5, yep. That one would be one right there. Those are our 3 stereocenters. Awesome. Any more questions on that one?
Nope.
Everybody good? Okay. Let's carry on. So we have the same molecule 4 different times. I should have put these on the same page. I apologize, but which numbering represents the correct priority for each group? Okay. So basically, which one has the 4 different groups around our stereocenter labeled correctly with our numbers? So what I'm going to do is just redraw the molecule a little bit bigger so that we can look at it better, and then we'll go to which one is correct. So we have okay. So what are our 4 different atoms bonded here? We have an oxygen, we have a carbon, carbon, carbon. Okay, so oxygen is going to be our number 1 for sure. Okay, now we need to write the 3-letter codes for each of these carbons. So let's start here. This carbon is bonded to what? Does anybody know?
The oxygen.
Oxygen, what else?
2 hydrogens.
2 hydrogens, perfect. Because it's got these 2 hidden hydrogens right here, right? Okay, so you're only looking at, most people would be tempted to write the hydrogen here, but that's not the hydrogen that we're talking about. We're talking about these two hidden hydrogens attached here. Okay. Now the 3-letter code here is going to be what?
Carbon and hydrogen.
Carbon and hydrogen, okay. The rule is when you have a double bond, you can count that as 2 of those elements. So we can count carbon twice for a double bond. And then there's 1 hidden hydrogen, okay. Just a little trick there. If it's a triple bond, you can count 3 different carbons, okay, for that triple bond. And then our 3-letter code here is carbon, carbon, hydrogen as well. Okay, so do we have our second priority group? Yes. Oxygen is higher priority than carbon. Perfect. So now we're here with these 2 carbons are identical. So now we need to move to this carbon, and we can move to either one of these carbons. We'll just go to this one. Okay. And again, with double bonds, a little trick is you can move back for 1. So now the 3-letter code is going to be 1 carbon and 2 hydrogens. Okay, so you can only go backwards for 1 on a double bond. Okay. And the trick to kind of know is there's going to be 2 hydrogens here on the end. So that's how you know how many hydrogens there's going to be. And then you can assume the other carbon. Okay. All right. And then the 3-letter code up here it's a CH3, so it's just going to be H, H, H. So now we know our higher priority is our group to the right. So this is going to be our number 3 and our number 4. Everybody okay with that? Okay, so now we need to find which one is numbered correctly. Which letter is it?
B.
B. Perfect. Any questions on that one? We okay? All right, carrying on. So we're going to designate each of the chiral centers in the following compound as R or S. Okay, so we have 2 chiral centers or 2 stereo centers. We need to label them as R or S. Okay, let's start with number 1. There is a hidden hydrogen here. Okay, then we have carbon, carbon, carbon. We'll start with our 3-letter code. What functional group is this? Does anybody know?
Carboxylic acid.
Perfect. Yep, it is a carboxylic acid. So carboxylic acid looks like this, right? Got a carbon double bonded to an oxygen, single bonded to an OH. Okay, so our 3-letter code for this carbon is 2 oxygens because it's double bonded to that oxygen, and a 3rd oxygen because it's single bonded to that one. So 3-letter code for carboxylic acid carbon is OOO. Okay. Our 3-letter code for this carbon on the right is carbon, hydrogen, hydrogen. And this one on the left is just 3 hydrogens. Okay, so now we can prioritize these. We know oxygen is highest priority, so that's number 1. This is going to be our number 2 and our number 3. We come out here because our number 4 is not in the back, and we move it to the back. Now our number 1 is going to be on a wedge. We say clockwise is pseudo R, which means our original is S. Okay, so we know number 1 is S. We can get rid of B and C. Okay, let's carry on to our second chiral center. What's going to be our highest priority?
The oxygen, OCH3.
Yep. What functional group is that, the OCH3?
Is it aldehyde? No.
No, not quite. It looks like that if you were to draw a stick. What is it?
Ether.
Yes, ether. Perfect. Just a little side trick there. Make sure you're staying up on your functional groups. Okay, so that's an ether. We've got a hidden hydrogen going to the back. And then let's write our 3-letter codes for our 2 carbons. So this carbon is bonded to 1 carbon and 2 hydrogens. Okay. And this carbon is bonded to 2 carbons and 1 hydrogen. So we know our higher priority group is going to be to the right. This is our number 2 and our number 3. Our number 4 is already going to the back, so we don't need to do a pseudo. We just determine that it is going in a clockwise direction, which means our number 2 is R. So number 1 is S, number 2 is R, and that means our correct answer is A. Any questions on how I got that?
No.
Everybody okay?
Mm-hmm.
Excellent. So we're going to label all the stereocenters in the following molecule. I'm just going to run through these super quick because there's quite a few of them.
Mm-hmm.
So again, just remember your rules for stereocenter. It's a sp3 carbon. Okay, so it has to have 4 different groups, no double bonds or triple bonds. It can't be a CH2 or a CH3, and it has to have 4 different groups around it. And especially in large molecules, you're pretty much always going to have different groups. Okay, so we're going to start here. This is our first. This is another one. There's another one. Here, 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 here. And what do you guys think about this one? Let's talk about this. Is this a stereocenter? The one I circled?
I feel like it is.
Yeah. Anyone else have anything different? I agree. It is. Perfect. So there's all our stereocenters. Again, we can ignore our CH2s. All of these are CH2s, CH3s, and then this one would have a hydrogen on it as well. It's actually a sp2 hybridized carbon because it's an aldehyde. And that's CH3 as well. So the dots are, yes, they are stereocenters. The circles are not stereocenters. I may as well just erase them so I don't confuse anyone. Okay. Carrying on. You guys got this. Nothing too crazy. All right. So we want to do the IUPAC name for this molecule. Okay. This is bringing back our exam 1 stuff, but you need to stay up on this information. It's very important. Dr. Garg's exams are very much cumulative. Okay. So don't forget the stuff from exam 1. He will test you on it again. Okay. So we got to label our longest carbon chain, and we want to number it with the lowest number substituents. Okay. So I know that my number 1 is going to be over here. And going up this direction will give me my longest chain. Okay, so that's our longest chain. We have a 3-ethyl. We have a 4-tert-butyl. We have a 5-ethyl. Okay, which one comes first alphabetically? Tert-butyl or ethyl?
Tert-butyl.
Tert-butyl. Why is it tert-butyl?
Because it's for the B.
Perfect. Yep. So our B is our key here. Okay, we alphabetize according to the B in our tert-butyl. Okay. If you remember tert-butyl and sec-butyl as your exceptions. Okay, let me draw a sec-butyl for you guys. Here's a sec-butyl. Oh, that was horrible. Okay, here's a sec-butyl, like that. Both of them are spelled with dashes, so you count the B for your alphabetical order. All of the other ones, if it's isopropyl, isobutyl, none of those are spelled with dashes, okay? Tert-butyl and sec-butyl, those are your exceptions, and if it's spelled with a dash, you go with the B. If it's not spelled with a dash, you go with the first letter, so I for iso, okay? So just remember that. Okay, so we've got 4 tert-butyl. Okay, what comes next?
3,5-diethyl.
Perfect. Because we have 2 ethyls, we need to do 3,5-diethyl. And then our parent chain is octane, because it's 8 carbons long. Any questions on how I got that? All right, moving on. I'm sorry I'm having to go so fast, everyone. It's just, I want to make sure that you see an example of all that you could possibly see on your exam. So, all right, so we want to determine which of the following molecules is or are chiral. Okay. So in order to be chiral, it needs to have a stereocenter that does not have a plane of symmetry. Okay. So what do we think about this first one? Does it have a stereocenter?
Yeah.
Yes. Okay. So our bromine is the top of our stereocenter. And is there a plane of symmetry in this molecule?
No, not really.
No plane of symmetry. So this one is chiral. Right. Talk about the second one. Do we have a stereocenter?
Yeah.
Yeah, we actually have 2, right?
Mm-hmm.
Right. Is there a plane of symmetry? The only one I could really possibly see is that, but no, 1, the groups are different, and 2, one's on a dash and one's on a wedge. So there's no plane of symmetry. So yes, this one is chiral. Okay. Let's talk about this one. Is this a plane of symmetry?
Yeah.
Yes, it is. Okay. So that makes it achiral, right? And does anyone remember the rules for it to be meso?
I don't remember.
Anyone else remember? Come on, there's 5 of you here. Anyone remember? Tricky question. Okay. Meso means that there are 2 chiral centers. So we have 1, 2, but there's a plane of symmetry, which makes it achiral. Okay. So this is meso achiral. Okay. It would just be achiral if there was a plane of symmetry, but for meso, it's a plane of symmetry and there's 2 chiral centers, 2 or more, I should say. Okay. So again, with this one, we have 2 potential stereocenters, but there is a plane of symmetry, so that makes it meso achiral. If we were to have, let's say, trying to think of the molecule. Okay. This is our potential stereocenter. There is a plane of symmetry, so that makes it achiral, but there is only 1 stereocenter potential, I should say, so that makes it not meso. So it's just achiral. Does that make sense to everybody? We okay?
Mm-hmm.
Julio. Which functional group is not present in the following molecule? So what I'd like to do is go through and label all the functional groups that we see, and then whichever one isn't there, we'll choose that, okay? So people, you can put it in the chat or you can unmute yourself. What groups do we see?
Aromatic's pretty obvious one. First one.
And then there's the amine and the amide.
Okay, so we have an amine right here. Right. Again, this is an amine because nitrogen is hiding behind this is an amide, sorry. I apologize. This is an amide because the nitrogen likes to hide behind the double bond O. Amide hide. Okay. Nitrogen hides, so it's an amide. Whereas this one is an amine. And he's mean, so oxygen doesn't want to be around him. Okay. So that's an amine. Okay. What degree amine is this?
Second degree.
Perfect. 2 degree amine. Okay. And any other functional groups?
Ether.
Ether. Perfect. This is an ether. All right. So which functional group is not there?
Ester.
Ester. Beautiful. Thank you for the participation on that one, everybody. All right, so we want to add all lone pairs that are missing in this molecule. And if there's charges that need to be there, then we'll add the charges too. So let's talk about the nitrogen. Is there a missing lone pair?
Yep.
Okay. Just one. How about on this oxygen? Any lone pairs missing?
2.
2 sets of lone pairs. Okay, do we need a charge?
No.
Nope. That's not coming out very good, I apologize. Okay, no charge there. How about this bottom oxygen? What do you think? How many missing lone pairs?
Just 1.
Just 1 set of lone pairs, right? Okay, because if you had any more, it would break the octet. But do we need a charge here?
Yeah, it's positive.
Positive. This oxygen has a positive charge because oxygen wants to own 6 electrons, and right now it only owns 1, 2, 3, 4, 5. So 6 minus 5 equals positive 1. That's how we get the positive charge. Okay. How about this carbon up here? What do we think? Do we need to add any lone pairs?
Nope.
Nope. Okay, so it's got its 2. How about a charge?
Negative charge.
Negative. Okay. And that's because carbon wants to own 4, and right now it owns 1, 2, 3, 4, 5. 4 minus 5 equals negative 1. So that gives it the negative charge. How do we know how many bonds something wants, or how many electrons something wants to own?
Look at the what it is called, like the Roman numeral.
Yeah.
On the periodic table.
So it's the columns, right?
Columns, yeah.
So you got, I'm going to draw a horrible looking periodic table here, but you'll get the picture. You've got 1, 2, 3, right? 4, 5, 6, and I didn't draw enough. 7 and 8. Okay. So you want to look at the column that it's in. So for example, carbon is in column 4. So it wants to own 4 electrons. Okay. Oxygen is in the 6th column. So it wants to own 6 electrons. Okay. Just a little tip there. Watch out for that. Any questions on how we found formal charges or number of lone pairs?
Nope.
Happy days. All right, let's carry on. Consider the molecule cis-1-methyl-4-nitrocyclohexane. Which of the following is the most stable conformation? A, B, or C? Any thoughts?
Say C.
We got one vote for C. Anyone else?
Wait. Spoken too soon.
You can remove your vote if you want. Any other votes?
I don't know.
one's-
I was just like
It could
debating between B and C.
It's actually B. Change my vote.
Okay, we got one vote at B. And we've got like a half vote. Okay, and this one was changed. All right. So let's talk about this. First of all, you want the most stable conformation is going to be the one in which your largest group is equatorial. Okay. So the reason why Eli thought C was because, well, both of our groups are equatorial here, so more stable, right? But the problem is our problem asked for cis. Okay, they need to be going the same way. This amine group right here is going up, and this CH3 is going down. So that's trans to each other. Okay, so this isn't even a valid structure. Whereas here our nitrogen is going up, and this one's going up, the methyl group. So they are cis to each other. This one's going down, and this one's going up. So they're also trans to each other. So just by knowing cis and trans, you could find out it's B. But the other reason is because our NH2 is our bigger group, and it is equatorial in this position. So that's going to be our most stable conformation. I totally confused you guys, didn't I? We okay?
Yeah, that's good. Thank you.
Okay. All righty. Let's carry on to this next problem. Which of the following are constitutional isomers of cis-1,2-dimethylcyclopentane? Okay. So first we're going to want to draw our cis-1,2-dimethylcyclopentane. Okay. So first of all, what's our parent chain?
The
The ring, I guess.
Yeah, how many member ring is it?
5.
Perfect.
Single.
Perfect. Then we have cis-1,2-dimethyl. So we can put them at any position. I'm just going to make this carbon 1 and carbon 2. Okay, and they're both going the same way, which means, you know, you could put them both on wedges, you could put them both on dashes. Whichever way you do it, just make sure they're both the same because it's cis. Okay, they're on the same cis, same side. Trans is opposite sides. Okay, so there's our molecule that we're looking for, and we're looking for constitutional isomers. Okay, so we're looking for, what is a constitutional isomer, first of all? What's the definition? Same molecular formula, but a different connectivity. Okay. So we're looking for something that has the same molecular formula but different connectivity, meaning that it's, you know, for example, this group down here is C7H14, right? You can go through and count how many hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Perfect. C7H14. So we're looking for ones that are also C7H14, but they are not the same connectivity. Does that make sense? That means things are moved around, you know, different carbons are connected to each other. Anyway, so we're going to look at that. So what do we think about this first one? Is this same molecular formula but different connectivity?
Yes.
Yes, it is, right? All we did is we moved one of the methyl groups over a carbon. Okay, so everything's going to stay identical except one of them gets moved over. So yes, this one is a constitutional isomer. Okay, what do we think about this next one?
I don't think they'll have enough hydrogens.
Okay, let's count them. We have 2, 4, 6, 8, 9, 10, 11, 12, 13, 14.
Oh,
14 hydrogens and 7 carbons. So C7H14, which means yes, this one is a constitutional isomer. So be very careful on the exam. They can look very different from each other and still be constitutional isomers. So make sure you write out the chemical formula and go from there. We okay?
yes.
So let's do the same thing on the next one. 2, 4, 6, 8, 10, 12, or 11, 12, 13, 14. So 14 hydrogens, we have 1, 2, 3, 4, 5, 6, 7. 7 carbons and 14 hydrogens, which means this one is also a constitutional isomer. Okay. Let's look at this last one. We have 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. C7H14. So this one is a constitutional isomer as well. The reason I made them all constitutional isomers is I wanted you guys to see that they can look very different from each other and still be constitutional isomers. Okay?
Mm-hmm.
If I had this molecule, okay, and we had something like this, how are these related? Are they constitutional isomers? That's right, they are stereoisomers. Okay, because the molecular formula is the same, the connectivity is the same, but the direction of our functional groups, okay, are different. Okay, so that makes them stereoisomers of each other. We okay there?
Mm-hmm.
All right, carrying on. So we want to match the IR graph to the molecule. So what I like to do on these is look for we're going to label the graph first, and then we'll look for one that matches. Okay. What does this 1600 tell us?
Mm-hmm.
I know this is a new topic. This might scare you a little bit. Okay. Anything close to 1600 is going to be a C double bond C. Okay. Does anyone remember 1700 in the 1700s? 1700s are a C double bond O. Just keep that in mind. All right, then we've got just below 3000. What is this?
Just below. Is it aldehyde?
No, that would be if there were like 2 peaks at 28 and 2700.
Oh, okay.
And they'd probably be stronger than this as well. They'd be something like that. Okay. Closer to the 50 mark. Okay, this is our sp3ch bonds. Okay. So that's basically your carbon that is sp3 hybridized bonded to hydrogens. Okay. Then what about this 3100?
Is it alkene?
Yeah. So that's going to be, yeah, it's basically your sp2chs. Okay, just above 3000. All right, and then what about 3400? One peak at 3,400. What does that tell us?
Is that just your like SPCH?
No, not quite. One peak at 3,400.
Is it a nitrogen or nitrogen hydrogen?
It is. It's an amine, right?
Yeah.
Okay, but what type of amine? Is it a 1 degree or a 2 degree?
1 degree. No, 2 degree. Wait, one peak.
2 degree amine, okay? Because a 2 degree amine has one hydrogen. I like to think about it as their number of peaks equals the number of hydrogens. You tell me that's not the reason, which that is true. That's not the reason there's only one peak, but if you think about a 2 degree amine, it's only got one hydrogen, one peak. That's how I like to think about it. Okay. If you want to think about it another way, figure out how to do that, but we got a 2 degree amine. We have sp2CH bonds, sp3CH bonds, and a C double bond C. So which molecule do we have?
A.
Perfect. Why can we eliminate C and D immediately?
Because there's no nitrogen in them.
Yep,
No
no
amine.
nitrogen. What else? There's a very unique property that C and D have in.
Oh, they don't have that big, that like longer peak, I guess, because like more like a curved thing
Yeah.
that the alcohols do.
Alcohol groups create a big, broad peak that's very to the left in our graph, very far this way, okay? Because we don't have that, we can eliminate C and D because there's no OH stretching, okay? Again, OH would look something like that, okay? And then we can eliminate B because there's no C double bond Cs, whereas A does. How was that? Was that scary? Nothing too crazy? We okay?
It's just good practice more.
Yeah.
Practice more, recognize the patterns.
We've got lots of examples here, so we'll go through some more in just a minute. Okay, so we're going to want to label the stereocenters as R or S, and then we're going to label all of the functional groups as well. Okay, so let's start with labeling stereocenters. Here's our stereocenter. We've got a hydrogen going to the back, which is our number 4. Bromine is going to be our number 1, and we've got this carbon and this carbon. Which one is a more higher priority?
Left one.
Left one, because the 3-letter code is carbon, carbon, carbon. Okay, the double bond counts as 2, and then this carbon. And then this one has 2 hidden hydrogens, and it's bonded to a carbon, so carbon, hydrogen, hydrogen. Okay, so we know our one on the left is higher priority, so this is our 2 and our 3. Our number 4 is already going to the back, so we can just go like this. So what letter are we? RS. Counterclockwise is
Yes.
S. Perfect. Okay. The reason I'm erasing so much is because I don't want us to get confused when we start labeling functional groups. Okay. So that's an S. Now we've got this stereocenter. Okay. Now we want to label our different groups. So we've got nitrogen, hydrogen, and 2 carbons. So our nitrogen is going to be number 1 and our hydrogen number 4. This carbon or this carbon going to be higher priority?
The left would be higher. The bottom one, lower one.
So it's 2 and 3. Okay. So again, our number 4 is going to the back, so we don't need pseudo. This is going in the counterclockwise direction, which means what?
S.
S. Beautiful. Any other stereocenters in the molecule?
Is there one one on the top left of the square?
Yes, there is. Perfect. Okay, that's another stereocenter. Okay, we're bonded to a hydrogen, which is our number 4. Okay, and then we got carbon, carbon, carbon. So let's write our 3-letter codes. This far right one is bonded to nitrogen. and 2 hydrogens. The bottom left carbon is bonded to 2 oxygens and a nitrogen. And the top one is bonded to carbon, hydrogen, hydrogen. Okay, so what's higher priority, N or O?
Oh,
O, right? So we know our OON is going to be our number 1. NHH is going to be our number 2. And CHH will be our 3. Our number 4 is not going to the back, so we're going to come out and redraw it. Swap it with our 3. 1 and 2 the same. Our pseudo is counterclockwise, which is what?
S.
So our original is R. Perfect. Any other stereocenters in the molecule?
I believe so.
Anyone see any? Nope, good to go. All right, so now we want to label our functional groups. Obviously, we have our aromatic rings. What else do we see?
Ketone? Or would that be amide?
It is an amide. Okay, this is an amide. You got a nitrogen, which is bonded to a carbon, which is double bonded to an oxygen. Doing too much talking. All right. So that's an amide. Any others? He hasn't taught you guys this yet, but for your, later on when you go to take any entrance exams to grad school or anything like that, this is a bromo. Bromo group. If it was a chlorine, it would be chloro. Iodine would be iodo. Okay. Just watch out for those if you're going to apply. All right, let's move on to the next one. What is our base peak in this graph?
72.
Perfect. So our base peak is always the highest or tallest peak. All right. So our next question is, what atoms or atom do we know is present in this molecule?
Would it be nitrogen since it's an odd number?
Perfect. Our mass number, okay, this is our mass number, is odd. Okay. And anytime you have an odd mass number, you know that nitrogen is in the molecule. Perfect. Okay, so we have a mass number. We know we have a nitrogen. Let's try to draw this thing. Okay. All right, so we need to have our molecule weigh roughly, right, it needs to get to 87, okay? Does anyone know how much nitrogen weighs?
It's 14.
14, perfect. How about carbon?
12.
Okay, and hydrogen?
Just 1.
1, perfect. So we know we have 1 nitrogen. Let's guesstimate how many carbons and then we can readjust. Let's say, let's go with 5. I don't know, we're gonna guess. Okay. And then, so then our mass is 14, 12 times 5 is 60, right? So let's try, we don't know how many hydrogens there's gonna be, but let's just try to draw a molecule here. So we've got a 5 carbon chain, and then a nitrogen. Okay. And if this was our molecule, we'd have hydrogen, hydrogen, So we'd have 2 hydrogens, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So does 14 plus 60 plus 13 add up to our 87?
Yeah.
Yes, it does, right?
Yeah.
Perfect. So this is our molecule. I just guessed on roughly how many carbons I thought there would be. If you guessed 4 and you came up short, add another carbon, see how many hydrogens there are, and double check again, okay? So you want to work through those. That's how you kind of think about this, right? Another structure you could get here is with the nitrogen in the middle, where it looks something like this. Again, that still has your 13 hydrogens, 5 carbons, 1 nitrogen. How are these two related?
Constitutional.
They're both C5, H13, and constitutional isomers. Right. Let's draw 2 resonance structures and the hybrid of the following molecules. So I'm going to go ahead and just draw a box here. It's going to be for our hybrid. So what I like to do with resonance structures, as I told you all in the last exam review, is to look at what's unhappy and how can I fix it. Okay. So what's unhappy in this molecule is a carbon that has a negative charge. Okay. What electrons can I move around to make that carbon happy?
I can change the double bond on the oxygen to a lone pair.
You're saying move these up here?
Yeah. And it would kind of trickle down along the side. So you get 2 double bonds inside of the ring.
Something like that.
Mm-hmm.
Okay. Well, let's first start with what's immediately on our carbon. Okay. I think that'll help us focus on it more. You're right. That's eventually what we're going to do. Okay. But what is right here at this carbon? We've got a hydrogen. Okay. We've got a set of lone pairs and our bonds here. Okay. So what we want to do, if we were to move electrons towards this carbon, then it would make it even more unstable. Okay, so this carbon is wanting to get rid of the excess electrons that are making it negatively charged. Okay, so we're going to take these electrons and dump them into this bond right here, okay, which in turn breaks the octet for this carbon, so it also needs to release its electrons and put them onto that carbon. Okay, so that's all we did. Okay, so we're just gonna do something like this. We now have a double bond right here. We have a set of lone pairs. And this is all the same, right? We didn't do anything here. What's going on at this carbon right here now? Does it have a charge or are we good?
Got a charge.
Charge, right? Perfect. So now our bottom carbon is totally happy. He's like, sweet, man, I got to dump those electrons. We're good to go. But now this carbon is unhappy, right? He's got a negative charge now. Again, we want to say what's unhappy and how can we fix it? Well, this carbon's unhappy. We don't want to move electrons towards it because that'll just make it more negative. Okay, so we're going to want to dump these electrons into a double bond right here, which in turn would break the octet here. Right? So we need to break this double bond and move them up onto the oxygen. Okay, so again, simply we're just going to draw our molecule. This double bond stayed there. There's now a double bond there. Single bond oxygen, which is now negatively charged. Okay, there's two resonance structures of our molecule. Did everybody follow that okay? Did it make sense all right?
Mm-hmm.
Any questions on how I got that? Again, just follow those simple steps. What's unhappy and how can I fix it? Are we going to want to move electrons towards it, away from it? Okay, those are the simple steps you got to go through. If it's negative, you want to move electrons away from it. If it's positive, you want to move electrons towards it. Cool. So now we need to draw the hybrid. So a hybrid structure is basically taking all your components and putting it into one. And you want to draw the least number of things, I guess is the way I'll put it, as possible around each atom, okay? So first of all, we have our oxygen here. The least number of bonds we have between our carbon and our oxygen is 1, okay? In this structure, there was only 1, but at some points there were 2. So what do we need to put here?
Dash line.
Perfect. That means there's a partial double bond there, okay? How about number of lone pairs on our oxygen? What was the least number of lone pairs our oxygen held in any of these structures?
2.
2 sets of lone pairs, okay? So we're just gonna draw 2 sets of lone pairs. And how about the charge? Did it always hold a negative charge?
No.
No, so it's just a partial negative. Okay, let's move along. This bond right here between these 2 carbons, okay, right here. Was it always just a single bond or did it ever have a double bond?
Had a double bond.
Yeah, it had a double bond. So we draw a dashed line. Perfect. Same thing for this carbon-carbon bond. There wasn't always a double bond there, but there was at one point, okay? And the same for down here, okay? All right. What's the least number of lone pairs that were held to this carbon in any of our structures? Zero, okay? Because here, there was no lone pairs, none, right? So we're gonna leave that. There's no lone pairs there, but how about charges? Do we need to put a charge there?
Mm-hmm.
Okay. So at one point there was a negative charge here at this carbon. At some points it was neutral, so there's a partial negative there. Okay. And is there anywhere else that needs a partial negative?
Yes, the bottom one.
Bottom carbon, right? Any other lone pairs we need to add? Any double bonds? How's it look?
Looks good.
Okay, that's our hybrid structure. Any questions on how I got that?
Nope.
Cool. Let us carry on. So we're going to determine how each of the following molecules are related. Okay, so they're either going to be enantiomers, diastereomers, constitutional isomers, identical, or different. Okay. So what do you guys think for this first one?
They're identical, the first ones.
They are. How do you know that?
Because they're just both, you can just like flip it around like a pancake.
Yeah. So if you were to take one of these molecules, right, and pick it up off the page and flip it over like a pancake, then they would line up perfectly. Okay, so these are identical. If you were to label R as R and S on each of these, which I'm not going to do, but let's say this is R, this is R, these would also be the same. I'm not saying they are R, they might all be S, but whatever it is, they're all going to be identical, so that's how you know they're identical. If you're having a hard time seeing it, okay, then just go through and label it as R or S, and then you'll be able to identify it. Okay. All right, for the second one, we want to convert our chair conformation to skeletal structure. Okay, so I'm going to label this carbon 1, 2, 3, 4, 5, 6. All right, carbon 1, we have a methyl group facing up. And at carbon 3, we have a methyl group facing down. Okay, so this is our structure. What do we think? How are they connected?
1 is going up and 3 is going down.
Okay, so they're almost opposite of each other. So what does that make us think? If they're completely opposite, what does that make them?
This.
Starts with an
Oh,
E.
sorry, trans.
Okay. Are they diastereomers, enantiomers, constitutional isomers? What do you think?
Oh, so they're identical.
No, they are enantiomers. Okay.
Oh.
Because if you were to look at this, okay, if you were to take this one and rotate it onto here, then the carbon here would be on a wedge and this one would be on a dash. Okay, so they're exactly opposite of each other, which means they're images of one another. Okay, they are non-superimposable mirror images, which means they're enantiomers. Okay. I know it's kind of confusing, but again, if you're confused, write R and S, okay? Let's say this one's R and this one's S. This one would have to be S and this one would have to be R, okay? And then you'd know, because each of them are opposite of each other, they are mirror images, they are enantiomers. Okay. How about this next two? All right, if we were to take this first molecule, pick it up off the page and flip it like a pancake, okay?
Oh, it'll be the same thing.
It'd be identical, right? Because right now the bromine is coming towards us. If we were to flip it over, it'd be going away from us, so they're identical. Now, if you were confused, again, label it as R, okay? And then do the other one, and it would be R as well. They might both be S, they might both be R, whatever it is, they would be identical, okay? So you have the same molecular formula, the same stereochemistry, that means they're identical. It's a little tricky one, okay? How about this next one?
I think they're enantiomers.
Enantiomers, right? Okay. Because they are non-superimposable mirror images. If you held a mirror up to this molecule, this is exactly what you'd see, right? Off to the side of this molecule, you'd see that right in the mirror. Okay, you can't superimpose these. So these are non-superimposable mirror images of each other. All right, this last two. Let's write how many carbons and hydrogens. Okay. We got 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. C7H14. Okay. Let's do it for this next one. 1, 2, 3, 4, 5, 6, 7. C7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. C7H14. That means these are constitutional isomers. We okay on all those?
Mm-hmm.
Cool. All right. So now we've got two graphs. I know these are super hard to see. I apologize. I had to find these online, and anyway, I'll try my best to label them as we go. Okay. So here's our 1500 mark. So we can erase all that. Okay. What is this just below 3000? We got sp3chs. Okay.
Mhm.
How about these two peaks right here? What does that tell us?
The amine.
Yeah, it's an amine. What degree amine?
Would that one be a 1 degree then?
Yep, perfect. 1 degree amine has 2 hydrogens attached to it. We've got 2 peaks. Okay. And then he hasn't talked to you guys about this yet, but if you see kind of a broad peak just above 1500, you can ignore it. Okay. Because it's like an extension of the fingerprint region. In some molecules, sometimes you get a little bit of an extension beyond the 1500 mark. Okay, so if you see a broad peak there, then you can just ignore it. Okay, so we know we have a carbon chain, which has carbons and hydrogens, and we have a 1 degree amine. Okay, so now let's go down to our mass spec. What is our mass number here?
59, I think.
Yep. It's 59. What does 59 tell us?
That it has a nitrogen.
Has a nitrogen. Okay. And we already knew that because we have a 1 degree amine in our IR. Okay. So that just confirms that yes, we have 1 nitrogen in our molecule. Okay. So now we got to put all this together. Hint number 1, we have a 1 degree amine. Hint number 2, we know there's a nitrogen in our molecule. And sp3chs are pretty much in every molecule. Okay, so now we want to say, all right, well, we need our total mass to add up to 59. So we know we have carbons, nitrogens, and hydrogens. Carbon weighs 12, nitrogen weighs what?
14.
14, perfect. Hydrogen weighs 1. Okay, we've got 1 hydrogen, so we know that's going to add up to 14. Let's guesstimate how many carbons we think. What do we think? What should be our number? Let's go with 4. Okay, I don't know. We're going to try it. 12 times 4 is 48, right? Already we're added up beyond 59. Okay, so we know it's not going to be 4 carbons. Let's try 3. 36 plus 14. We're well below our 59 limit. Okay, so now we say, okay, we know we have a 1 degree amine and a carbon chain with 3 carbons. So let's add our 3 carbons, and then we'll add our 1 degree amine. This would have 2 hydrogens on the end, which is perfect. That's a 1 degree amine. We have 2 more hydrogens here, 2 and 3. So that's 2, 4, 6, 7, 8, 9. 9 hydrogens. 36 plus 14 is 46, 59. So that adds up. So this is our structure. Cool. Another way you could have drawn it is like this. Okay, that's still a 1 degree amine with 9 hydrogens. We kind of seeing how to work through these now? A little more comfortable?
Yeah.
All right. We've got 4 examples, so let's get moving on the rest of these. All right, so here's our 1500. I'm gonna get rid of that. And this peak is at 1712. What does that tell us?
It's alkene? Oh, sorry, no, actually, no.
No, non-alkene.
Carbonyl?
Yeah, C double bond O, right? If it's closer to 1600, it's C double bond C. Because it's closer to 1700, C double bond O. We have our sp3ch bonds. Okay, and these are all too small to say that they're anything. All right, so we can just ignore those. All right, so now let's go down to our mass number. I'm going to tell you this is at 72. Okay, so our mass is 72. Okay, so we don't have a lot of hints here, but we can still work through it. So we know we have C double bond O. We know our mass has to be 72. Is this an aldehyde? No? How do we know
I
that?
don't think so. Because you need to have like a more of a second pronounced spike.
Yeah, there would be a spike here at 2700 and 2800. Okay, there would be two spikes.
Yeah.
Is this a carboxylic acid, our C double bond O?
No, because it doesn't have that broad.
Yeah. So carboxylic acid shows a broad peak that goes through 3000. Okay. So we don't have that. So we know this is what type of C double bond O. What is it called? What functional group?
Ketone?
Ketone. Perfect. Oh, I didn't mean to do that in blue, but that's okay. All right. So we know we have a ketone, okay, because we knew it wasn't an aldehyde or a carboxylic acid. And those are the only three functional groups, okay, that have C double bond O's. Ketones, aldehydes, carboxylic acids. Okay, so we know it's a ketone, okay, and we know that our mass is 72. So let's go carbons that weigh 12, oxygen that weighs 16, and hydrogens that weigh 1. How many carbons do you guys think?
4.
Let's go with 4. I'm good with that. So we have 16, 48. 16 plus 48 gives us 58, 64. Okay. So we're going to get pretty close. Right now we're at 64 and we need to get to 72. So let's draw our carbon chain with 4 carbons. We'll draw our ketone. Okay. How many hydrogens are here? We've got 3, 5, 8. We got 8 hydrogens, which gets us to 8. 48 plus 16 is what again? 64 plus 8 is 72. So that checks out. So that is our molecule. Any questions on that one?
Mm-mm.
Cool. Let's carry on. All right, let me zoom in on this. All right, here's our fingerprint region. What is this right here? It's a little over 2,000. Does anyone remember? I don't blame you. It's a new topic that you guys are going over the last couple of days, but got to get ready for Thursday.
Is it an alkyne?
It is an alkyne, perfect. So it's going to be a C triple bond C or C triple bond N. Okay. Usually your C triple bond C is shorter than your C triple bond N, but it's hard to really tell for sure, so you don't want to assume anything. Okay. So we can just say, all right, let's go. It could be either one of those. We've got our sp3 CHs. Now what is this? It's a super strong peak at like 3,300. Someone know? Okay. because
Did it
it's
seem-
so strong. Sorry, go ahead. SPCH, is that what you said?
Yeah.
Nice, perfect. SPCH, okay? SPCH is a terminal alkyne, terminal triple bond, okay? So just keep that in mind. Again, we're not sure if it's nitrogen or carbon quite yet, but we know it's going to be on the end now. And then our mass number here is 68. Okay, so what does that tell us that it's not?
Nitrogen.
It's not nitrogen.
It's not a C triple bond N, okay? So now we can go down here and write all of our clues down. We know we have an alkyne and it's terminal. We also know that our mass is 68. So we don't have any clues that there's anything other than carbons and hydrogens here. We need our mass to equal 68. Okay, so we have carbons and hydrogens. How many carbons do you guys think?
4.
Let's go 4. Okay. All right, so we don't know how many hydrogens yet, but we're just going to draw 4 carbons. And then 1, 2, 3, 4, and we have a terminal alkyne. Okay. And here we'd have 1 hydrogen, 2, 3, 4, 5, 6. Okay. So we'd have 6 hydrogens. So right now we're at 48 and 6. Do those add up to 68?
Not quite.
Not quite. Okay. So let's go with a 5th carbon. 5 times 12 is 60. And hydrogens. We're going to add 1 more carbon here. So we'd have 1, 2, 3, 4, 5, 6, 7, 8. So that adds up to our 68. We have our terminal alkyne. So this would be our molecule. Does that make sense to everybody?
Mm-hmm.
Cool. So we had no hints there was anything other than carbons and hydrogen. We knew it was terminal because of this big bond, this big stretch right here.
I have like a question.
Yeah.
So I kind of thought the sp3ch could have been an aldehyde, but well, I mean we know it isn't. So like, what else could it be? Kind of stray away from that too. Is it the fact there's no CO double bond?
Yeah. So you would see a C double bond O here in like the 1700 region.
Oh, okay, cool. Thank you.
Yep. And it's pretty obvious when there's like an aldehyde peaks, like they're pretty pronounced, right?
Mm-hmm.
And they're not nearly as strong as the sp3CHs. Okay. So, those are 2 things that would help you. Cool. Last one, friends. Okay. So we've got our fingerprint region. Okay. This is at, oops. This is around 1600. Okay, so what does that tell us?
C double bond C.
Perfect. Then we've got just above 3,000 sp2CHs, and just below 3,000 is our sp3CHs. What is an sp2CH going to do in response like this, right? What does that tell us? They're just the hydrogens attached to that C double bond C, right?
Mm.
Okay. So just watch out for those. And then our mass number down here is 120, and 122.
Wouldn't that be a bromine then? Because it's like a 1-to-1 ratio.
Yep, n plus 2 plus 2. Yep, so we know that because it's a 1-to-1 ratio, we have a bromine. Perfect, I'm glad you guys remembered that. If it was 3-to-1 ratio, what would our molecule be?
Chlorine.
Chlorine. Perfect. So we know we have a C-double-bond-C. We also know there's a bromine. Okay. So our mass needs to add up to a total of 120. Bromine weighs 79 grams per mole. Okay, so we're definitely gonna have one of those. Carbons weigh 12, hydrogens weigh 1. How many carbons do we think? Your guess is as good as mine.
3.
Let's go 3. Okay. So we know we have a C double bond C, and we know we have a bromine. And we're going to go with 3 carbon chain. So let's add our double bond like that and our bromine here. Okay. So now we have a hydrogen here, and 2 hydrogens here. So we have 5. So move this over just a tad. We have 79 plus 36 plus 5. 79 plus 30 is 109 plus 6. It's 115 plus 5 is 120. So that checks out. And this is our structure. Nice job, guys. Any questions on any of that? That's the end of our review. Feeling okay?
A lot better now.
I think good examples, just kind of helped you get ready. Feel good?
Yep.
Awesome. Well, thank you for coming, everybody.